All right. Oh, shoot. Oh, okay, but this is the first example. Okay. So what we are doing over here is try to work through the problem number 5, okay, in the homework set 3. All right. And what we are trying to do is just try to calculate the, they say total energy entering the system by heat. Okay. So at this point, we're starting at the segments A to B. From A to B is a constant volume process. So, okay, let me rephrase this one more time just for the video. Okay. And for that, then W is definitely 0 because there's no work done. Volume does not change. First law of thermodynamics down to delta U equal to Q. And because we know that the delta U is 3/2 nR delta T, so that should be good. It's right there. All right. And a quick reminder, this can be written as the NC sub V delta T if you want. Then the final point is B, initial point is A. So it's going to be 3/2 nRT at B minus T at A right there. But then because we have a PV diagram, so the PV diagram can be read off from reading out the scales. So I can say nRT just PV. So I can take PBVB, subtract PAVA. And the rest just read off from the axis. And then what you get at point B is going to be 3 PIVI. From point A is going to be PIVI. And that's it. At the end, you get 4 segments A to B is 3 P sub I, V sub I. And the sign is automatic. That means what you're getting right here is a positive sign. That's a positive number. Positive heat means the heat is entering the system. So that means Q at this point over here is entering the system. And that is corresponding to the Q1 in this diagram right here. And you can see the arrow of this one is pointing inward, into the system. Okay, does that help? I guess. Okay, but then, all right, we might still stuck with a little bit of problem. Ajahn, they want the final answer to be in, oops, that's not supposed to be the effect here. They say that they want the final answer to be in terms of R and T sub I. Don't worry, we can sort of manipulate these terms very easily. The reason I said that because it's a 1 mole of gas. And you know everything already is there on a PV diagram. So that's why, right, there's nothing to worry about. Look at this, guys. At point A, let me put here, point A over here, the pressure is P sub I, the volume is V sub I, but from the equation of state, PIVI must be equal to nRT A. And that's supposed to be T sub I right there. And that is at point A. So that means the temperature at point A right there is a T sub I. So what I can do is just replace this temperature at A to be I. And because we know it's 1 mole of gas, so N right here is 1. So that is 1 R T sub I. All right, got that one? So you now know how to convert PIVI into T sub I. What I'm saying over here is PIVI is just going to be RT sub I, if you want to. So I mean, you can always write down everything in terms of R and T sub I. Okay, is that all right?
Okay.
I hope. All right, but anyway, in the exam, if it doesn't come as the parameters like this, if it shows up as a numbers, I think that's even make it, that's gonna make it even easier, because if these are all numbers, just plug in the numbers and then do the numerical calculations. Okay, but this one is kind of annoying a little bit. It's still stuck with the parameters like P sub I, T sub I, on and on. Yeah. Okay, try again. Keep going. So is this a good pace going like this? You guys still okay with this? It's a good review, I hope. All right. Okay, keep going. Let's try again together. B to C. Let's do B to C. All right, let's start from scratch over here. B to C. Now you can see that there is some expansion. So the W is definitely going to be non-zero. Yeah. But the good thing about this one is you can calculate the work done is just going to be, let me draw this one for you. I mean, highlight this one for you. It's just going to be area under the curve. There you go. With me, guys? From B to C. That is going to be area under the curve below BC segments. And it's just a rectangular shape. So you know the work done is going to be the height, which is the height of that BC line, times the volume change, the width of this rectangle. Cool. And we keep track of the delta, right? We always take delta to be final minus initial. So this is going to be, okay, read it off. It's going to be pressure at B. Yes. Or at C, they are at the same pressure. And then you do the final pressure, I'm sorry, final volume, which is at C caps right there at point C. Subtract out the volume at initial point at B. All right, the sign will be sort of reveal itself. Okay, and the good thing about this one is because you are expanding, the final volume is larger than the initial volume, so you can expect that the work done is going to be positive. All right, now read off the scale, guys. Pressure at point B is 3p sub I. So 3p sub I. Very good. Volume at point C is 2v sub I. Volume at point B is v sub I. So from here, what you are getting for the W is going to be 3p sub I v sub I. Just leave it there. All right. Once you're done with the work calculation, come back to your first law of thermodynamics, the delta U equal to Q minus W. And that means the heat is going to be delta U plus W. Does it look familiar to you? All right. And for those of you that sort of familiar with this already, you can actually wrap them up, jump right into the heat calculation, the Q, directly by saying that, well, Ajahn, I know the delta U is always 3/2 NR delta T. The W, actually, if you didn't want to calculate the value of the P delta V, you can say it's going to be P delta V here. And then you can use the equation of state, turn that P delta V into nRT. So that means you're going to have P delta V to be nR delta T. You guys with me? And that remind you what we had another formula for this heat during the isobaric process, the constant pressure process, to be 5/2 nR delta T. And that number 5/2 shows up here as up there is the molar specific heat for the constant pressure process. So that means if you know how to apply this relationship or this formula right away, you can jump ahead and then just like, hey, Dan, I can calculate the heat during the isobaric process by saying that the heat flow is going to be 5/2 nR delta T if you want to. All right, but I just want to showcase that, hey, I mean, you can start from the work calculation and then you add on top of that the delta U, you'll get to the heat anyway, right? It depends. Okay. All right. Once we have that, then keep going. No matter which path you take, it's just you're gonna come back to that 5/2 nR delta T anyway. So it's gonna be 5/2 P final, which is at point C, V final minus P initial at point B, and V at point B. Okay, still so far so good? All right, I'm using nRT equal to PV all the time here because we have the PV diagram. And that's it. Just plug in the numbers. You'll get 5/2. All right, I can, because running out of space at this point, but you can read off the scale. Just read it out here. At point C, the volume and pressure times together, you're going to get 6 PIVI. And at point B, you're going to get just 3 PIVI. Once you subtract them, you're going to get just 3 P sub I, V sub I right here. Got that? Very good.
Okay.
All right. And during this B to C process, your heat flow is going to be 15 over 2 P sub I V sub I. And then you can turn PIVI into RT if you want to, RT sub I if you want to. Okay, is this still with me? 7.5. Yeah, that's fine. You can write it as 7.5.
Okay.
Yeah. And once again, you can notice that this is a positive number because everything is, we keep track of the subtractions correctly in order. So this one give you a positive del, positive Q. Positive means heat flow into the system. So this is the reason why the arrow over here is going to be inward. And in this diagram, they call this Q sub 2, right? Q2 right there, heat flow into the system. Okay, very good. So I think this is actually the same as the one that we did in class because it's pretty much have a rectangular shape of the process. So that's why it probably look familiar to you, the way that we calculate this. All right, but I think this is a good review. There are only 3 terms that you need to calculate in the first law of thermodynamics. So it's running around here. All right, pretty good. So keep going, guys. All right, so I think I can split the screen a bit. Okay, let me use the, how to do that. Just, here you go. Split. All right, and I'm just gonna have an extra note here. There you go. All right. Okay, keep going. Oh, I think it's better to look like, oh, this looks new. Make it, don't use the dark mode here. All right, here we go. All right, so keep going, guys. Still having fun, I hope. Probably not, but I think it's not too bad. All right, let's move on to going from C to D. There you go. All right, now I have more space, so I should be able to just keep writing now. Okay, so from C to D, let me zoom in here. Okay, so from C to D, once again, W is 0. We might be able to go a little bit faster now because you sort of get to, you know, all right, I've seen this many times now. So the first law of thermodynamics says delta U must be equal to Q because W is gone. And that is going to be 3/2 N R delta T. Okay, and it's going to be 3/2 N R T final is point D. Initial point is C. Pretty good. All right, and then use once again the first law of the, not first law, the equation of states. So it's going to be 3/2. Okay, let me write it here as a P at D, V at D, subtract P at C, V at C. Very good. And plug in the value. At point D dog, D over here is a 2 V sub I. The pressure is P sub I. So it's going to be 2 P sub I, V sub I. Okay. At point C is the 3 P sub I, that's pressure, and 2 V sub I for the volume. So it's going to be 6 P sub I, V sub I. Very good. Okay, there's a question comes in. Can I just substitute A, B with negative sign? Okay, you will see. It's actually no. The reason is because the C back to D is happens at the different volume. Whatever going on from A to B, it's happening at V sub I volume. But right now you're doing, even though, I mean, it looks just like opposite process, but it's at different points on the PV diagram. So you cannot just substitute with the negative sign. Otherwise, then it will just cancel each other out. And that doesn't seem to be the case here because it's probably not going to be perfectly fit. I mean, they are not going to give you the same value. Okay, going from A to B and C, come back to D. Okay, So stick with this. What you have here is -4 in the brackets and divided by 2, everything turns negative. So it's negative here. And it's going to be 6p sub I v sub I. Okay. Is my math correct? I hope so. Okay. So as you can see that the negative value that you get is guaranteed that the heat flow that you are looking at right now is going to be in the opposite direction. The direction is definitely opposite. So the heat is actually going out because you get a negative heat flow. But the value of it, see, is 6. On the way in, if you look at the Q1 here is only 3. So you draw in the heat 3p sub I v sub I, but you take away the heat 6p sub I v sub I. So that's why we say you cannot just inverse the sign. Okay, they have the different value of the heat. Okay, but the good thing is the sign is automatic. That's already outward right there. Okay, so that's pretty good. Yeah, let me highlight this blue here. That's good. It's right there. Sorry, it's different software. Sorry, there. Okay. So that's Q3 in the diagram. Leaving the system, 6p sub I v sub I. All right, last one, guys. Almost done. D back to A. All right, now you can, of course, you can say, well, John, is definitely going to be the reverse of B to C, but at different value. Okay, now if I want to show you, if I want to jump right into the final value of the heat calculation, I can say heat during this process is going to be 5/2 nR delta T. Can you see how to apply this equation now? Because I know it's a constant pressure process, isobaric process. So I can jump ahead into the conclusion of the heat flow during this isobaric process right away. And I just say it's 5/2 nR T final is going to be at A minus T initial is going to be at D. And once again, nRT is PV. So it's going to be 5/2 P sub D, I'm sorry, P sub A, V sub A minus P at D, V at D. Very good. And once again, substitute the value into this. At point A, the pressure and volume is going to be 3PIVI. Very good. At point D, pressure and volume products will be 2PIVI. There you go. And that's it. You get a -1 in the bracket divided by 2. So it's -5/2 PIVI. Negative signs means the heat is leaving the system. There you go. That's your Q4 right there. That much. Okay, as you can see, the value is going to be the magnitude. The value of the heat will be different from Q2. Yeah. All right, once we have all these value calculated, now that's already answered part A and part B automatically. So in conclusion, you can name this if you like. So this portion right here is, okay, you can, I mean, according to the diagram, you call this part Q1. You call this part Q2. You call this part Q3. And you call this part Q4, according to the diagram. All right, so with this pretty much naming part A, your final answer will look like this. Part A, the total heat flowing in, the heat enter is going to be Q1 plus Q2. You guys with me? Let me put the magnitude there just so we don't have to worry about the sign. And in part B, heat that leaves the system is going to be equal to the Q3 plus Q4. So the diagram looks pretty good already. Yeah. But in the exam, probably I don't have that arrows for you. You're just gonna have like a rectangular shape process. All right, but from your calculation, you will be able to tell the direction of the heat flow automatically. All right. And part C is going to be automatic. The efficiency is going to be, well, oh, Dan, so this is good. So if you want, okay, before we get to the efficiency, you say, oh, Dan, it's just the work done over the Q hot. Okay, but now you will be able to calculate the W by saying that the W is going to be here. Watch carefully here. It's going to be heat enter, that's Q1 plus Q2. Subtract out the heat leave the system, that's Q3 plus Q4. Oops, sorry, two double brackets here. There you go. And then you divide it by Q hot, heat that flow into the system. It's going to be Q1 plus Q2. Got that one? Pretty good. All right. And then, of course, for those of you that are familiar with this, Bojan actually, revise again, because the W is just Q hot minus Q cold over Q hot for efficiency. You can do the division first. It's going to look like this, all right, the one in the slide that we talked about. So you can calculate the efficiency through the 1 minus the ratio between the discarded heat, the Q cold, over the incoming heat, the Q hot, if you want to. Anything is good, right? Because now you know the directions of the heat flow. So you do anything you like, that's fine. So your final efficiency will look like 1 minus, okay, Q cold is going to be Q3 plus Q4 divided by Q hot, the one that's entering the system, is going to be Q1 and Q2. All right, and that's it. You can start doing the summations. Q3 and Q4, there was, you just need the magnitude. So it's going to be 6 and 5.5. So let me do the numbers here. So it's 6 plus 5.5 PIVI. Okay, for Q1 and Q2 is right there on the left here. Let me zoom here. So for the Q1 and Q2, it's just going to be 3 and 15 over 2 PIVI. Just take the magnitude. You don't have to worry about the sign anymore. And it definitely has to be that your PIVI must cancel, because efficiency is unitless quantity. You're supposed to get just a number out at the end. All right. Once you work this number out, that is your efficiency of this engine. And it's done. A, B, and C. All right. It's a long, long one, but I am pretty sure that the exam will look like this. What else can I ask? I'm just going to show you or give you a diagram in PV diagram, of course, and just ask you this, like, hey, calculate this, calculate that. When I say this and that, what can it be? It's either the U, the Q, the W, efficiency, and we're going to dive into the Cardinal efficiency. So if you want to get to the Cardinal efficiency, how do you do it? Well, John, that's not bad, because how can I don't have more page here. Okay, here we go. So if I copy this here, so let me sort of draw one more time. So the diagram that you have, it look like this. And then you have a diagram, look like a rectangular shape over here, right? And the one thing that I always ask you to keep in mind was that, but hey, everyone, think about this as every time that you see the PV diagram, you always have an isotherm. The isotherm is the line that showcases the constant temperature process. So you have A, B, C points here at 4 corners. Each point must lie on an isotherm right there. Yep. Right. Remember this correctly, I hope. Something like that. All right. These 2 points might not be on the same line, but it's just maybe just my drawing right there. Just assume that this on the different line. Okay. And the higher lying line represent a higher temperature. So this is a high T, this is a T high. The lower lying line will be the lower temperature line. This is low. Okay, so part D, they're asking you the efficiency of an engine operating in a Carnot cycle. So this means you would like to replace this engine, the rectangular shaped engine, between the same temperature extremes. Here, the key is the extremes. So you have to be able to pick the lines that give you the extreme values between two temperatures. Yeah. So when you have that, well, Ajahn, that's not bad because we know where to pick. I know that this point will represent the highest temperature of this engine that is operating. And this lower left corner will be the lowest temperature point of this engine. So that means when you look at this one, you know, point C will be at the highest temperature and point A will be at the lowest temperature. So your Carnot engine, if you were to replace this with a Carnot engine, is going to be the engine that operating between two extremes temperature, T at A and T at C. So what you have is the efficiency of a Carnot engine. You put the subscript C into this, and it'll be equal to 1 minus, you remember? We can, okay, let me write. Efficiency in general is a Q cold over Q hot, right? We just showed you that. But then for the Carnot engine, it's so special that you can replace this ratio with the temperature. That's the thing. Wow. All right, remember this one, yeah? And then because we already picked which point representing the T cold, which point representing the T hot, so it's going to be T at A over T at C. Okay, okay, very good. All right, so your job is just, hey, Ajahn, so what is the ratio between these two temperatures? And once again, we recall the equation of state.
Okay.
What else do we do? All right, so what we do is, well, Ajahn, all right, so if you want a ratio, you do PA VA over TA equal to PC VC over TC. It's always the case for the ideal gas. All right, so the ratio that you want between A and C temperatures is going to be PA VA over PC VC, yeah, something like that. And now you can just read the scales. At point A, the pressure is PI, volume is VI, so it's going to be PI VI. At point C cat is 3 PI over 2, so it's going to be 6 PI VI. Definitely PI VI has to be canceled because at the end you want to get just a number, and that's it, guys. So what you have is just 1 minus 1/6, and that is just 5/6 efficiency. That is it, done. Cool. So that means if you replace, oh, your friend already gave us the numbers, about 19% for just a rectangular shape process, you get only about 19% efficiency. But then if you replace this with a Carnot engine that run between two extremes temperatures, you get up to 5/6. And that is like, I don't know, 80%, something like that. Yeah.
Question.
Yes.
When we say engine efficiency, do we compare to relative to Carnot engine or just in general with no respective to Carnot engine?
Come again?
I mean, if we say engine is 40% efficient, is it 40 efficient compared to Carnot engine, or is 40% efficient regardless with no reference?
You mean comparing to Carnot engine?
Yeah, or we don't compare.
Compare, I mean, compare. You can compare, I think. I don't understand your question.
I mean,
clearly.
I just wonder if กับไม้ขายจริงๆอีก 40% efficient
40% efficient if your car, okay, your car.
Yeah.
Okay.
And I wonder if it relative to Carnot engine or not. I mean if it relative to kind of engine อย่างเงี้ยดูวีกันเชกอีก 40% efficient or อีก 40% efficient to kind of engine do you get it?
Usually efficiency is just the number for that particular engine though.
Okay.
I don't think you need to compare across the type. I mean, one type is just a regular engine, right? And the other type is the Cardinal engine.
Yeah.
So it's the two separate engines actually. But you just say that we just know that the Cardinal engine is going to be the highest possible engine in theory that you can achieve.
I know.
Yeah, but I don't think, I mean, if you have a car engine that already run at 40%, that is your car. But then if you want to compare to the Cardinal, you have to completely replace your car engine with another kind of engine. Yeah.
Oh, okay.
Does that make sense? I don't think you can compare across is two different engine. So it's like run differently.
Okay.
Yeah. Okay. But it's just like, it's the question like this, just try to ask you about the upper limit. What is going to be the attainable efficiency if you were running with a Cardinal engine, which doesn't exist. It only exists in theory, something like that. Yeah. Okay. All right. So I hope this conclude. This is a good act. I mean, I always say this. This is the kind of question that you should be able to get at the end of the thermodynamics module. Like many weeks of studying supposed to lead you to this, because this is like a grand finale of the whole thing. It's like the reason for understand the heat, the work, first law of thermodynamics, how to calculate all the processes, and how to calculate everything from each process, eventually gonna lead you to the heat engine. And then once you get to this one is like a direct applications of those first law of thermodynamics, and that's it. So that's why asking you just to do this is already asking you everything about first law of thermodynamics automatically. So this is a good example, actually. All right.
Okay.
And I think pretty much I can guarantee you the final answer will, I mean, the exam will look just like this. I mean, not exactly like this, but you're going to get some engine process in the PV diagram, and then you just do the analysis like this. Okay, it's going to be the similar kind of analysis. Yep. All right, good. All right, even though you don't ask this one, if I have to pick like an example to showcase what is supposed to happen in the exam, I'm going to showcase this one anyway. So, because it's like a complete pictures of what we have been doing in the past month. Very good. All right, nice. So you just read my mind, asking me to show you this one. Okay, basically, if I am able to do this question, I should be able to pass. Oh, definitely, yeah. I think this is like better than pass. Actually, you should be able to just like ace this one. Well, but we have other topics too, guys. I mean, wow, I'm not just asking you the thermodynamics law. How about homework number 4? Okay, definitely. Yeah, we can go to homework number 4. Okay, let me pull that off. It's just like a short one. If I don't have this one, then you probably don't have any clue what type of question is going to show up in the exam. So that's why I posted this one, just like extra 2 questions in the homework set 4. Okay, so we can go through both of them actually, but I mean the key one is number 1. Okay, number 1 is a good one, because if you can get to the number 1, the rest should be good. An ice tray contains 500 grams of liquid water at 0 degrees Celsius. So that's good. It's just the liquid water, but at 0 degrees C. Calculate the change in entropy of the water as it freezes slowly and completely at 0 degrees Celsius. So this is exactly the question that I told you that we don't want to focus too much on the entropy, because we only spend like an hour talking about it, and we didn't really want to do a full calculation of this one. So that's why the question will be, I wouldn't say easy, because I mean, probably relative to the amount of time that you spend on this one It's just about it. This is about the question that I should be able to ask you, given the amount of time that we spend on this topic. So this one, just to testing, if you have a chance to try to calculate the entropy change using its definition. Okay, it's about latent heat. Yeah. So let's review the S, the entropy, we define to be the heat, but we said the heat need to be calculated from a reversible process. Yeah, because we discussed about the reversibility and irreversibility, the heat that responsible for the irreversible process is the heat that you cannot take it back. It's like a lost. It's like something has already been lost. And then pretty much sometimes you cannot control that loss. So that's why you only be able to calculate the heat from a reversible process, because that is a manageable heat. Okay, cool. So at least from what we have learned, try to calculate this heat from a PV diagram or some calculations, formulas, relationship that is, well, if you can write down the formula, so it's reversible. That's what we have been doing. So if you can draw a diagram, you can draw a curve in the PV diagram, you can write down an equation for it. We assume that is a reversible process, okay, over temperature. So this is definition of the entropy. However, once again, we don't want to do this by saying that, because heat is the energy transfer. So usually it's not just like it's not a value attached to an object. Heat is energy transfer. So that's why this will lead you to the change of the entropy. Okay, so that has to be kept in mind, that usually the way that you calculate is like, you can think of it like change of energy equal to the work done in first law of thermodynamics. You calculate the change of the internal energy, the delta U, not just the U itself. Same idea over here, but now it's just the ratio is with respect to the temperature. Okay, don't get the unit of entropy. Yeah, when you say you don't get, because it's not very familiar, but the units of this one is just going to be joule per Kelvin. This is a weird unit. So the bad thing about the entropy is it's not very common. Well, it's not common parameters that people use all the time. So this is too bad. Yeah, energy is easier to get because it's related to everyday lives and everything, but entropy is just confusing. It's so hard to understand. Yeah, it's rated one of the most complicated concepts to understand in physics, because there are so many ways that you can explain this, and there are so many things that entropy is sort of like touched upon. Like as I showed you a little bit about the data ability that a system can store data in it, it turns out related to entropy as well. Okay, so over here, let's come back. This one is a good starting point. You have a water. Okay, let me put it in a container or something. Yeah, and then you want to turn this into an ice. So let me put like in a blick like this. So you want to turn a liquid water into an ice. The good thing about this one is an easy calculation because temperature is constant. T is constant. When T is constant, your calculation is simple because you don't need any integral, you don't need any calculus. So what you can do is right away is just delta S. During this, it's a solidification process. You're freezing the liquid water into an ice cube. So you freeze it. The heat involved in this process is just, of course, is just latent heat. Yeah, that is the amount of heat that you have to take away from the liquid water. So over here is the heat amount is ml for sure. You guys with me? However, because heat need to leave the system, so actually this magnitude is going to be negative. You guys with me? We still use the same agreement. Heat flow into the system is positive, heat flowing out of the system is negative, because this one you want to extract heat from the liquid water out to freeze it down. So you want to remove some energy from the liquid water. So that's why this negative ml has to be here. So the energy leaving the system in form of the heat is the negative value. and equal to the latent heat of fusion minus ml divided by the temperature, and the temperature happens at 0 degrees Celsius. You can turn this into Kelvin by add 273 to it. So that's when you put it there. And that's it, guys. You can take mass to be 500 grams. You put it in kilogram. That's 0.5 kilogram. L of this one, you can look it up in the table. And I don't remember it myself. It's like 300 something. All right. But anyway, that's L for the water divided by 273 Kelvin. Done. That's it. So cool. And the good thing about this one is you say that, hey, Azan, entropy change is negative. What does it mean? It means the entropy of this water is reduced. It's cooling down. It's reduced. But about Azan, wait a second. You already discussed about the second law of thermodynamics, that the entropy always increase, or at least the best it can do is just no change. How come this one has a negative change of the entropy? The key is this is the entropy change of the water. Okay. The key of the second law of thermodynamics say is the change of the entropy of everything in the universe. In the universe. So what I'm saying over here is, if you really want to calculate the total change of this entropy, you have to take into account the environment, and that's everywhere else outside. So what I'm saying over here is heat leaves the system. So it means heat leaves the water. Some heat leaves the water. It has to enter the environment. You guys with me? Q system. Let me put like this. It's like one is from the system. There's a heat leaves the system, but the heat that leaves the system actually has to enter the environment. It has to go somewhere. So if you look at the environment, there is a heat flow into the environment. So there is a positive change of the entropy of the environment. And if you sum up everything, it's going to either no change or positive change. Okay, got that one? All right, so for this particular one, they just want to calculate the entropy of water, just of water. So that's why it's negative, because it turns into solid. So it's smaller entropy. Yeah. Okay, that's a question. And the environment is cooler than the water. It depends. I mean, for this particular case, I would expect that the environment is supposed to have a higher temperature. Yeah. But anyway, you still have to calculate the whole thing. So we need more, how can I say it? The complete description of the whole environment for you to be able to calculate the change of everything. Yeah, but right now, this is just a focus on water, and that's easy to calculate. So, okay, I hope you guys get the feeling of how to calculate the entropy from the first problems. Let's attack second one. Okay, second problem. Suppose the N mole ideal gas in the figure expands to 4 times its initial volume. For this process, the initial and final temperature are the same. Good, good. So this is isothermal process. Calculate the entropy change for the gas. We can do the calculation. This is a hint. Using the isothermal process between the initial and final states of the gas. All right. Actually, just to make this sort of more general, I shouldn't put the parentheses here. That was like a clue, but the reason that it has to be here because that's exactly what we did in class. Okay, so let's do it one more time because we're gonna review everything. So let's review this one. All right, guys. First, I'm gonna show you with this. Let's draw a PV diagram for this, shall we? We need PV diagram anyway, so we can relate everything. Okay, so you have an N mole of an ideal gas, and then it expands 4 times at constant temperature. So let's say that first, at point number 1, the gas is at volume. Let me call this V0 somewhere. And let's say the pressure is somewhere called P0 as well. And that is the point number 1 right there. You guys with me? So that is going to be initial point in the PV diagram. And then eventually this one expands 4 times. So it's going to come out here for V naught. But because everything is under constant temperature, P1 V1 over T1 equal to P2 V2 over T2. Because temperature already constant, they cancel out. The product between P and V must be fixed. So if you have volume 4 times as big, the pressure must be 4 times smaller. So it's going to be somewhere here. P naught over 4. You guys with me? That is point number 2. Okay, cool. But then we said entropy is path independent. So actually, I don't care. I don't care how you bring the system from 1 to 2. You can bring it in any process, any direction, any path you want. The entropy change stays changed at the same amount. Okay. Remember the one that we talk about, the MGH. You can bring it up, MG1. You can bring it zigzag, whatever is MG1. You can throw it in, throw it back, MG1. You can go up and down. As long as the initial and final points are exactly the same, any path will lead you to the same amount of change of energy. Same thing happens with the entropy. Entropy is also another values, another parameters that path independent. So we take advantage of that, and that's whatever it's saying in the parentheses. You can connect between these 2 points using any path. And because we already discussed this, we want to be smart. They are lying on the same temperature. They must be somehow on the same isotherm. If they are on the same isotherm, we're going to connect these 2 lines using isothermal process. With me? And this is going to be easy to calculate because temperature is constant. We love it. When temperature is, oh no. Oh, I just used super zoom here. Okay. I thought I already entered a new page. Okay, so over here, so that's good. So constant temperature is we love constant. Okay, so what we want over here is, there you go, temperature change delta S is, because this one is sort of like, temperature, heat flow, and blah, blah, blah might look a little weird. So let me put it in terms of the differential form for now, from 1 to 2. Here we go. So I just turned the heat flow into a differential heat dq divided by the temperature. Okay. Very nice. Okay, and now because we're connecting these 2 lines using the isothermal process, we have already learned from first law of thermodynamics, during the isothermal process, delta U is 0. Yes. No energy change. So the first law of thermodynamics say Q must be equal to W. Yes, very good. And the W is going to be integral P dV. Okay, this is a good review for the isothermal process as well. And the integral of P dV is going to be just the area under the curve right here. We did that in class right there, if you want. But for us, we don't need to go through the heat calculation. All we need is just a tiny change of the heat, a tiny change. So you can just take the P dV along with you. That means what we want is just what is going on during an infinitesimal change of the whole thing. Don't need to integrate just yet because we don't want to figure out the total amount of heat. We want the dq over T. So that means I can just keep going. Equal. Color looks so weird. Equal P dV over T from 1 to 2. You guys with me so far? All right, I'm just extracting the dq. It's just a general properties of an isothermal process. The heat exchange must be equal to the work done, but because the work done can be done like in a very small change, so we just take the differential form of this one, plug it in here. dq is just p dv. And then now we use equation of states, PV equal to nRT all the time. So I can say P over T, PV equal to nRT. So P over T is just going to be nR. Okay, very good. PV over V, sorry. That's what I thought, like, hey, V is missing. So P over T is going to be nR over V. So good. Just nR over V dV from point 1. But now point 1 is just V naught. Point 2 is 4 V naught. See, I am writing everything down in terms of the volume variable now, the V. The N is constant. I can pull it out. Oops, sorry. N is constant. I can pull it out. R is constant. I can pull it out. I have only 1 over V left to integrate. The integration of 1 over V is log of V. And I can just say it's a V initial to V final. And that's it, guys. N R log 4 V naught over V naught. And it's just N R log 4. Done. Very good. Okay, nice. Okay, and once again, this one just showcased that we don't know much about the rest of the environment, but what we can tell is this one is the entropy change of the gas, expanding 4 times its initial volume isothermally, but it doesn't matter isothermal or not, I don't care. It's a natural log, it's natural log, Ln is an Ln. Yep. Okay, so with this, and then what we did in class was we assumed that this expansion happens in a closed environment. So if you remember, if insulating wall over here. So if everything is happening in an insulating wall, so that means there's no heat exchange, nothing is going on. So when there's no heat exchange, so that means your environment doesn't feel a thing. So your environment is just like, oh, I don't know what is going on in there. I don't care. So environment does not feel any heat. There's no heat entering the environment. So that means the entropy change of the environment is 0. The only thing that is changing is just the system itself. So that's guarantee one thing, that if this whole thing happens in this insulating wall, the net delta S net is just going to be the delta S of the system. And you just say it's nR log 4 and it's greater than 0. So that's good.
Okay.
So when they say it's good, means you got the net positive change of the entropy. And we say this process is, well, is an irreversible process. But this is not totally fair, but I think this is it. I mean, the figure over here is like it's a movable piston. But when we say it's irreversible process, mean it's irreversible process in itself, by itself. The direction of it is once it expands, it won't be able to contract back by itself. But of course, you can put your hands and press it there, provide some work done, and then you can reverse the whole thing. And that's go back to the first law of thermodynamics. But in the second law of thermodynamics, if the expansion of the gas happens inside the insulating wall like this, the entropy change is positive. And this is correspond to your everyday experience. When gas already expands, well, it's not going to contract back by itself. Yeah, even though it can be done, but not by itself. So what if question give pressure instead? Okay, there's a question comes in. What if question give pressure? That is fine. So as long as the question give you the pressure, you can still use the same argument here, bringing from point 1 to point 2. I mean, by having the volume increase 4 times, the pressure has to decrease 4 times. So you still end up with the same PV diagram anyway. Yeah, so that's still okay.
Okay.
As long as you give one of the other, I mean one of the two, either P or the V, you will get to the same conclusion on the PV diagram. Yep, should be good. All right. So I hope having you guys try these two questions, I hope you can at least worry less about what kind of question about the entropy will be. I'm going to ask you like a basic question. Maybe if it's some integral, it's going to be the integral that require just like this, just like a one-step integral. And then you just do a simple integration from point 1 to point 2. And then you end up with the logarithmic function, or maybe just a simple form of the function that you need to integrate. Yeah, so don't worry too much. And I'm just gonna sort of have you give it a try. How can you calculate the change of the entropy? Yeah, but maybe I'll give you a little bit more complicated, just a little bit, so you can relate what is going on in the real world. Maybe like something that you can relate to, and something that we can at least apply the second laws of thermodynamics principle on top of it. And then you hopefully you see some connections there. I think that's it. All right. It's not going to be like super crazy question or anything. All right. And you have 12 hours to try. So just give it a shot.
Okay.
Yes.
Okay.
Question? Yes.
Question. Properly got on the exam, but the question is that got inverted isochronous exchange. If I were to draw from point A to B, do we have a isochronous line that flip?
The common line?
No, isothermal.
Isothermal, okay.
That is flip in reverse. Okay, possible?
Reverse mean reverse in direction, or you flip?
No. Flip. Yeah, transform. Yeah.
Transform. I think I don't get what the.
I mean, yeah, flip. Let's say we got what call? I
Right
mean,
now, what we're going here, right? We're going downward like this.
yeah.
Yeah. When we say flip or transform, what is the flip?
The flip is let's say you put point to
Uh-huh.
no. You draw a oval shape. You get the idea, right?
An
Oval shape.
oval?
Yeah, oval. Okay.
Like this?
Yeah, exactly.
You're asking, is it possible to do this line instead?
Yeah.
This, something like that?
Yeah.
Yeah, you can.
But is it inefficient or something?
Right, because I have no clue what this line is.
No, okay.
The problem is, if you come up with another whatever line, the problem is this line here, you have to figure out the change of the heat, right? And that's going to be a little bit harder for you to try. But I mean, the answer will be yes, you can still be able to do it. But then the problem is now your change of the heat from the first law of thermodynamics, all right, is going to be the change of the internal energy plus the work done. Now, the good thing about picking the isothermal process is this term is pretty much disappear from your equation. So you can calculate the dq very easily by looking at the area under the curve, which is just the work done. But now if you pick some weird curve, then yeah, you can still do it. And you're going to end up with the same value anyway.
I mean,
I can actually propose an even easier one that you can actually calculate though. Why don't you do this? You do isobaric process, and then you follow by constant volume process. That might be able to, I mean, it's doable because that one we know how to calculate perfectly for each segment. But you will find out that it takes you a little bit of time and stuff, and then eventually you arrive at the final same problem. I mean, same answer in RT log 4, in R log 4. Yes.
Okay.
Yeah, you can try. It's a good try, actually. If you want to do it, that would be nice, I think. Yeah, but you can pick any line you like. You can draw like a straight line, any curve, circle, oval, anything. Yeah, eventually you arrive at the same conclusion, but it just take you more time and harder way, and there's a harder calculation to get to the answer. Yes. Okay, very good question, actually. All right. So more questions, but I think I think this is already a very good question. The big two questions that you asked, that's already summarized everything. The other parts in the exam will be like an introduction, like maybe the heat calculation, calorimetry, thermal expansion. That will look very easy in relative to the heat engine problems. Yeah. Or like work calculate, I mean, first law of thermodynamics and applications. And we end up with the entropy problems. Right. I'm pretty sure you guys will be fine.
Okay. Okay.
It's gonna be okay, right? And especially it's open book and you have like 12 hours to try. You can even just wake up at noon and then look at or start the problems like 4 o'clock in the evening. You still will be able to do fine. Okay, just give you a grand conclusion, but I'm gonna type it down. But at least for those of you that's here, so to once again, just to confirm, I'm going to release the exam paper at 8 o'clock tomorrow. Is that right? Is that too early? 9 is better. All right, but anyway, I'm gonna release at 8, and then you have 12 hours, okay, for you to complete that one and submit at 8 p.m. Okay, that's the whole thing. Yep. And just you can do any way you like. You can type it down. You can use your pen and pencil, write it on a paper, put it, I mean, use your iPad, whatever, write on the screen, everything. But at the end, I just need your final file to be a single PDF file. That's all. Just easier, easier than just submitting in terms of like a JPEG or some photo, and then I have to collect them, put them into like a single file. It's just gonna take a lot of time and maybe some mistakes there. So just combine them into a single file. That's all I'm asking. Yeah. But you can type it, write it, scan it, whatever you like. Anything is good. Okay, sounds good. All right, so I think that's good. Oh, any other more questions? Oh, that was okay. I think did I answer all your chats? Okay, pretty good. Okay, so any further questions? I think you guys looks pretty good from the question you asked. Seems to be very confident. Maybe it's mind confidence here. Okay, is there anything that thermodynamics can't? I think so. Yeah, there are so many things thermodynamics cannot explain. We are in the, I mean, we are just part of the thing. After this module, we'll start looking at waves. That's definitely the part that's thermodynamics. Well, it doesn't mean it cannot explain, but it's just different part of the nature that we want to describe. And that's outside the scope of thermodynamics. So it means if you're asking something about heat, about temperature, about thermal properties, then that's going to be your thermodynamics. But if you want to ask about, let's say, force, like you want to kick something, you want to pull something, that's going to be Newton's, that's going to be Newtonian mechanics. And later, after the first exam, if you want to talk about something oscillating, vibration, some movement that's a periodic, then we're going to have some treatment for those. That's going to be waves. Okay. And then if you want to talk about electricity, magnetisms, some interactions due to charges, particle, and everything, that will be electricity and magnetism. So as you can see, so thermodynamics has its scope. It's not going to go beyond the scope of heat and temperature. Yeah.
Final question, okay?
Yeah.
So, what I learned from lesson here is that if I going to melt or anything, it have to be, I mean, I can only be at 0 temperature, 0 degree. And if I add more heat to the other side, it's going to melt faster, right?
Yes. Yes.
Okay. And let's say that I have something very hot, super hot.
Super hot, yeah.
and I put a lot of ice into it. And in cohort the couple to melt, the ice couple to melt, co-far is not possible. What will happen? You can add a limit to how far can ice melt. In yeah.
Well, yeah, I would say limits probably no, but when you get super hot,
Okay.
the energy is super high, then you're gonna disintegrate the molecular structure of the ice anyway. So the way that you imagine the process will change. It's not gonna be thermodynamical process anymore because thermodynamics needs equilibrium, needs slow and steady change. But what you are doing over here is going to create like a crazy, very complex dynamics. And that's going to need something else to explain.
Oh,
does that make sense? So thermodynamics needs to be, slowly, everything has to be quasi-static. You have to be able to treat the properties of the system properly. You have to, what is the temperature, on and on. But once you get something super hot with something super cold, once the process starts, what is your definition of temperature of the system? It's gone. I mean, because some part of the thing was super hot, some part is super cold. There's no average structure of there's no average value of the whole system anymore. So you lose the main characteristic of thermodynamics system. Yeah. So you need something else. Yeah. I would say no. I mean, there's no limits, but you just need something else to explain. I think that's my take on it. All right, guys. Sorry, give me, there was a quick, give me 1 second. 1 second. Sorry, just some alarm coming up. Okay. All right. So that's my take on it. All right, guys. So I hope this is good. If you have any other questions, from today and tomorrow, if you have further questions, the line is still always on. And for tomorrow's, once the exam is on, I will post I think the time that I'm going to be here to answer your question. So my plan is this. So tomorrow around 10 to 12, the same time as this one, I will have a Zoom sessions on just in case. Once you have already read through the problems a little bit, maybe a couple of hours. And if you have any questions, if you want to discuss, or I have the channel open here just in case. All right. But if not, that is okay. But at least there's a way that you can communicate verbally with me tomorrow after you have already seen the paper. So I will post a Zoom sessions I will post like a link to the Zoom sessions, maybe around 10 to 11 or so, something like that. And beyond that, my line communication is always open. So I will check periodically just in case you have any question during the day. Okay, sounds good. Alrighty, guys. Thank you so much. And then good luck in the exam tomorrow. You guys will do well. I am pretty sure. But if not, you still have 2 more exams to whatever. Try it. You still get A. I hope you guys all A here. Thank you. Oh, thank you very much. Yeah, cool. All right. Thank you, Kap. I'll see you tomorrow. Maybe not face to face, but you will see my exam paper tomorrow. Okay. Bye-bye, guys. Take care.